Hello, and today we're going to learn how to solve logarithmic equations. There's two ways that we can solve these depending on how they appear. If they appear in the form of log of something is equal to a constant, we can rewrite the logarithmic equation as an exponential equation, where now our independent variable would be isolated and we can solve for it. If, however, the log is equal to another log and they have the same base, then we can set the arguments m and n equal to each other. That was one of the laws of logs that we learned earlier. With logs, because there is a restriction on what you're allowed to take the log of, your arguments have to be bigger than 0. There is a possibility that you can get extraneous solutions, so we just got to make sure we check for those. I'm going to check for them by stating a domain, or at least a rule that would give you the domain of the logs from the beginning. So for example, before I start, I noticed that I have 2x's on the inside of a log function, which means that 2x has to be greater than 0. And this one's actually easy to solve for. X has to be greater than 0. So if we solve for this, the only values that we're allowed to actually keep are ones where x is greater than 0. So let's see what happens when we solve this. I have a log equal to a constant, so I could rewrite this as an exponential. The base of this log is missing, so it's a common log. The base is 10. So I'm going to rewrite this as an exponential with the base of 10, like my log function. And then these switch places because when you rewrite a log as an exponential, you're really rewriting it in its inverse form, and inverses switch your independent and dependent variables. So this would be 10 to the first power is equal to 2x. So 10 to the first power is just 10. And then if we divide both sides by 2, we get that 5 is equal to x. This satisfies the domain restriction of the log function on the left. X has to be greater than 0, and 5 is greater than 0. So x equals 5 is the only solution that works. Let's take a look at this one. Here we have two logs equal to each other. They're both natural logs, which means both of them have a base of e. We're going to be able to set the arguments equal to each other in a second. First, let's just look on the inside of here. So x squared minus 3 is the argument, which means that x squared minus 3 has to be greater than 0. Therefore, x squared has to be greater than 3. I'm just going to leave it like that for right now. In the other log, we have 3x plus 1, and so therefore that has to be greater than 0 to satisfy the domain restriction of a log function. Subtract 1 from both sides, so we have 3x is greater than negative 1, which means that x has to be greater than negative 1/3. Okay, so we have our little domain restrictions going forward, just things to look out for. Alright, let's actually start to solve this thing. So both of these have a base of e, which means I can set the arguments equal to each other. So x squared minus 3 is equal to 3x plus 1. This looks like a quadratic, so I'm going to set everything to 0 so I can try to factor it. So x squared minus 3x minus 4 is equal to 0. I can factor this into x minus 4, x plus 1 is equal to 0. Therefore, x is equal to 4 and negative 1. Alright, now let's check these against the domain restriction. So, 4 squared is greater than 3. That works. 4 is greater than negative 1/3, so x equals 4 is a valid solution. Negative 1, if I plug that into here, negative 1 squared is not greater than 3. So automatically this number fails this part of the domain restriction. But let's just see what happens if we plug it into the other one too. Negative 1 is greater than negative 1/3. No, it's not. It's less than negative 1/3. So negative 1, if it fails once, it's not allowed to be accepted as a real solution. But just showing you how I would check them both. Anyways, alright, so this is not a real solution. X equals 4 is the only real solution that exists for this equation. Let's move on. Alright, here we have neither of the two initial setups that we said we were allowed to have if we wanted to solve. We don't have a log equals with constant. We don't have a log equals a log. Instead, we have two logs on one side, two logs on the other. Okay, this is why it's important to know how to expand and condense log expressions, because notice all of these have a base of 2. So if I wanted to, on the left, I could condense this into one log function. These are two logs being added together. When you add two logs with the same base, you can rewrite it as one log with the arguments being multiplied. So 5 times x minus 1, which would be 5x minus 5. Okay. On this side, you could look at this two ways. One, you can use the law of logs, saying that if two logs are being subtracted with the same base, you can divide their arguments. So x divided by 1 would just be log base 2 of x. Another way of thinking about this is this guy right here you can actually evaluate. 2 to what power is equal to 1? The exponent that this is equivalent to is 0. So log base 2 of x minus 0 is just log base 2 of x. So whether you use the that quotient law of logs or just evaluate this and get 0, either way, this is what you end up getting. Now notice that we have a log equal to a log. They have the same base, so we can set these guys equal to each other. The arguments, that is, 5x minus 5 is equal to x. I'm going to subtract x for both sides, get 4x, and add 5 to both sides. Yep. And then divide both sides by 4. X equals 5/4. Alright, let's see. X minus 1, which is the argument from this guy right here, has to be greater than 1, greater than 0 rather, which means x has to be greater than 1. 5/4 certainly satisfies that. 5/4 is 1 1/4. Up here, your argument is x, so x has to be greater than 0, and sure enough, 5/4 is greater than 0. So this solution is not extraneous. It works in all the cases where you have the variable x inside of a log function, so this is your solution. No extraneous solutions. Alright, we're going to do one more. Here we have a log equal to a log, but notice that the bases are not the same. What that means is we cannot set x minus 12 equal to 9. Instead, we have to find some other way of solving this log equation. Notice, though, that there's no variables here. These are all numbers, so we can see if it's possible to evaluate what is log base 3 of 9. And it is something that's easy to evaluate. What is the exponent you have to raise 3 to in order to get to 9? That would be 2. So this log expression is equivalent to 2. So really, we can rewrite this as log base 4 of x minus 12 is equal to 2. Alright, and now we have a log equal to a constant, therefore we can rewrite this as an exponential. The log base is 4, so the exponential base is going to be 4 as well. These switch places because when you rewrite as an exponential, you're really writing using an inverse function, so which means your independent and dependent switch. So we have 4 squared is equal to x minus 12. 4 squared is 16, so 16 equals x minus 12. If we add 12 to both sides, we get that 28 is equal to x. Alright, if we look back up here, what was the domain restriction? X minus 12 has to be greater than 0, which means x has to be greater than 12. That's our domain restriction. Our solution is indeed bigger than 12, so it satisfies that condition. There you have it. Those are the two different ways that you can solve logarithmic equations.